So in section 2.1, we studied one type of polynomial function, right? We studied second-degree polynomial functions, which can also be referred to as quadratic functions. So in section 2.2, we're going to be studying polynomial functions of higher degrees. So here's our definition, which we looked at before, of a polynomial function. So basically, we have a string of terms where every variable is raised to a non-negative integer, so to a whole number exponent. And we look to the largest exponent, which if the polynomial is in standard form, it's going to be this first exponent, so the largest exponent, to determine the degree of the polynomial. And the coefficient of the term, where you find the degree, is known as the leading coefficient. And the degree of the polynomial and the leading coefficient is going to help us today with sketching the graphs of some polynomial functions. All right, so the characteristics of the graphs of polynomials. So all polynomial functions have graphs that are both continuous and smooth. So continuous, meaning that you can trace the graph of a polynomial throughout its entire domain, which is all real numbers, without ever having to pick up your pencil. And smooth, meaning there are no sharp corners to the graph. So an example of a sharp corner would be like the graph of absolute value of x, right? That's the graph that is the V shape, right? So that would be an example of a sharp corner. So polynomials do not have any sharp corners. They are both smooth and continuous. Now, in calculus, you guys are going to look at some more formal definitions of continuous and smooth, but for now, we're just going to use these intuitive definitions. Okay, so we're going to be determining the real zeros of a polynomial function, and all of these statements are related, but I just want to clarify the vocabulary. So x equals to a is a solution, let me switch this, is a solution or a root. Those two words are interchangeable to the equation f of x equals to 0. So if you're solving an equation, the value that you come up with for x ends up being the solution or the root. From knowing the solution or the root, you also know the x-intercept of the graph of the polynomial is going to be a comma 0, right? An x-intercept is a point on the graph, so it can be represented as an ordered pair. Now, zeros, I think the term 0 and solution or root often are interchanged, and really a 0 ends up corresponding to a solution or root, but we say that x equals to a is a 0 of the function because when you evaluate the function at a, you end up with 0. And if x equals to a is a 0, then you know that x minus a must be a factor of the polynomial f of x. So let's just look through a quadratic quickly. So f of x, for example, f of x equals to x squared minus 4. Well, if we set f of x equal to 0, okay, and then we wanted to solve for the solutions or roots, we could add 4 to each side there. Could also factor. And we get x is equal to plus or minus 2. So plus or minus 2 are both solutions or roots to the equation 0 equals to x squared minus 4. Now, from those roots, we also know now that -2, 0 and 2, 0 are x-intercepts. For the graph of f of x. And we also know that if we were to evaluate the function f at -2 or at 2, we would end up with 0. Therefore, we can say that x equals to 2, -2 are zeros. And they're real numbers, so we can call them real zeros. We also know that because 2 and -2 are zeros, that we can rewrite the function x squared minus 4 in its factored form, x minus 2 times x plus 2. Okay? So this is helpful because when the value of a continuous function transitions from negative to positive or vice versa, it must pass through a 0. So through 0, the x-axis, right? So if the function is going to change signs, sign change is going to occur at the x-axis. But it's also important to remember that the existence of a 0 does not imply that the function changes signs. It's just if there is a sign change, it will occur at at the x-axis. So for example, you guys are familiar with the graph of y equals x cubed. Okay, so to the left of its x-intercept at the point 0, 0, the graph of x cubed is negative, meaning the y values at the points on the graph to the left of 0 would be negative, and then to the right would be positive. An example of a graph that you guys are familiar with where there isn't a sign change at the x-intercept would be x squared. Right, to the left, the graph is positive. To the right, it's also positive. So this leads to the intermediate value theorem. So I'm going to draw a picture to help demonstrate what the intermediate value theorem is saying. And for now, it's just going to be important that you understand what the intermediate value theorem says. And then next year in calculus, you guys will do more with the intermediate value theorem and you'll actually prove it. Okay, so the intermediate value theorem says that let a and b be real numbers such that a is less than b. Okay, so I have these two x values where a is less than b. And let f be a polynomial function. So I'm going to draw a polynomial function that is smooth and continuous. So this is going to be f. If f of a and f of b have opposite signs, then there is at least 1 0 between a and b. So let's think about what this means. So this would be, this point on f would be the point a comma f of a, where the y value over here would be f of a. This point would be b comma f of b. So basically the intermediate value theorem says that if you pick two x values within the domain of a polynomial function, where one of those x values is going to be less than the other, and their corresponding y values have opposite signs, like one is positive, one is negative, then there's going to be at least 1 0 between A and B. There could be more because the graph could end up crossing the x-axis more than one time, but there will be at least 1 0 between A and B. Okay, so we are going to find the zeros of this polynomial function, and we're going to rely on our Algebra 1 way of identifying these real zeros. So we're going to set f of x equal to 0, and we're actually going to solve for the roots of this polynomial equation first. And then remember, the roots will end up corresponding to the real zeros of the polynomial function. So notice that this is a third-degree polynomial function, and there's a GCF. The GCF is x, so I'm going to factor x out. And then this quadratic factor will also factor to x, what is it, plus 4 minus 1. So we can see that the roots, which will end up corresponding to being the real zeros, real meaning they're real numbers, will be 0, -4, and +1. Now, as an extra, from knowing these real zeros, you could also identify the x-intercepts for this graph, right? There will be an x-intercept at 0, 0, -4, 0, and 1, 0. Just as a little bonus. Now, sometimes polynomial functions have repeated zeros. So looking at this equation down here, this factors to be x minus 1 times x minus 1, which can be written as x minus 1 squared. So we also call, when we're solving the equation, right, we refer to this as a repeated root. X equals to 1 would be a repeated root, which would then correspond to being a repeated 0. So x would equal to 1 and 1. We don't usually list, if it's a repeated root, we don't usually list them out the number of times they occur. It's not wrong to, but we're going to actually be stating the multiplicity of the 0 once we've determined if a repeated 0 occurs or not. So the multiplicity of this 0, so the 0x equals to 1, the multiplicity is 2 because it occurs twice. Okay, so if x minus a raised to the n power is a factor of the polynomial f, then a is called a 0 of multiplicity n. So this polynomial function is already in factored form, and we want to list the zeros and state their multiplicities. I'm going to show you 2 different ways you can do that. Remember, whenever the exponent is not written there, we can assume it's being raised, the factor is being raised to the first power, and the term is being raised to the first power. Okay, so our zeros are x equals 0, -2, 3/2, and +5. And some of those zeros are repeated. So the way that I'm going to write this is the multiplicity. So the multiplicity of 0, 0 has the factor where we determine that 0 is a 0 is x, and it's raised to the first power, so there's a multiplicity of 1. -2 has a multiplicity of 4. 3/2 has a multiplicity of 5, and 5 has a multiplicity of 1. Your textbook writes your zeros and their multiplicities like this. So they would list 0, mult 1, -2, mult 4, 3 halves molt 5 and 5 molt 1. You can choose either way. Okay, so adding the multiplicities yields the degree of the polynomial. So let's go back up here and focus in on this polynomial. Now, if we were to multiply out x plus 2 to the 4th, that factor, so x plus 2 times x plus 2 times x plus 2 times x plus 2, that all multiplied out would make that factor a 4th degree polynomial. And then 2x minus 3 raised to the 5th power, that multiplied out would give us a 5th degree polynomial factor. And then x minus 5 is just 1st degree, and x is just a 1st degree. So if we were to multiply them all out, we would end up with an 11th degree polynomial. The degree of the polynomial f is going to be 11, and we can figure that out from just adding up all of the multiplicities. So f of x is an 11th degree polynomial. So if the polynomial is in standard form, so completely expanded, you look to the term with the largest exponent. If the polynomial is in factored form, you can add up all of the multiplicities, so all of the exponents of the factors. Okay, so we want to find a polynomial of degree 6 whose zeros are such with the multiplicities listed. So let's call this polynomial g of x. Okay, so if negative 3 is a 0, that means that x plus 3 is a factor, and it has a multiplicity of 1. You don't have to write the 1 though. If 5 is a 0, x minus 5 is a factor, has a multiplicity of 2, so I'm going to have an exponent of 2. And then if 0 is a 0, that's x minus 0, or just x, and has a multiplicity of 3. So I'm going to clean that up and write this as x cubed times x plus 3 times x minus 5 squared. The order of the factors does not matter. That's by the commutative property of multiplication, right? A times b is equal to b times a. So we're going to be sketching the graphs of polynomial functions, and these are the steps that we're going to be following. So we're going to determine the end behavior, and we'll talk about how to do that in a sec. Finding the real zeros, which will correspond to the x-intercepts. Determine the multiplicity of the real zeros, which we'll talk about why we're going to do that in a second. Determine the y-intercepts, so you can just set x equals to 0 and solve for y. And I am not going to I used to make them do test points. You can to get a little better picture of what the graph looks like, but I'll explain once we get to our first graph why I am not going to require you guys to use test points between your x-intercepts. All right, so end behavior is basically what's happening to the graph as x approaches positive and negative infinity. Like, what are happening to the y values of the points on the graph as x gets infinitely large or infinitely small. So if you were to zoom out on a graph, what does it look like is happening? And a polynomial will actually end up having the same end behavior as the term that you go to determine its degree and leading coefficient. And the reason that is as x gets just infinitely large, you can think about the terms of the polynomial being at a tug of war with each other. And as x gets bigger and bigger and bigger, that term with the largest exponent is going to end up dominating that tug of war every time. Or the same thing happens as x gets infinitely small, so x approaches negative infinity. That term with the largest exponent is going to end up dominating the others so that the others are pretty much insignificant. So our polynomial will end up having the same end behavior as whatever y equals to a sub n times x to the nth power is. So we have this little chart to help us organize end behavior, the possible end behaviors. Okay, so if n is even and a sub n, so the leading coefficient, this is the degree, this is the leading coefficient. If the degree is even and the leading coefficient is positive, an example would be y equals x squared, then the graph will have the same end behavior as y equals x squared, so both ends pointing up. So we say as x approaches positive or negative infinity, the y values for the function will end up approaching positive infinity. If the degree is even but the leading coefficient is negative, so for example y equals to negative x squared, end behavior will be both ends pointing down, where we can say as x approaches positive or negative infinity, the y values will end up approaching negative infinity. If the degree of the polynomial is odd with a positive leading coefficient, the end behavior will be the same as like y equals x cubed, or even just y equals to x, so like a line with a positive slope. So as x approaches positive infinity, the y values would approach positive infinity. Oops. And as x approaches negative infinity, the y values would end up approaching negative infinity. Now, odd degree polynomial with a negative leading coefficient, like y equals negative x cubed or y equals negative x, same end behavior as a line with a negative slope. Okay, so as x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches positive infinity. Okay, so if a 0 ends up having an even multiplicity, then the sign is not going to change for the graph, and therefore the graph will kind of bounce off or touch the x-axis at that x-intercept. And if the multiplicity of the 0 is odd, then the graph will end up changing sign and will cross through the x-axis at that x-intercept. Okay, you can think like x squared versus x cubed. All right, so first, let's think about what the degree of this polynomial is. And it's in factored form, so we can just add the exponents up. So 2 plus 2 give us 4. It's a fourth degree polynomial. If that were to be multiplied out, the leading coefficient would end up being a positive 1. So for end behavior, I have to drop this. So for end behavior, even degree polynomial, positive leading coefficient, it'll be both ends up. So we'll be able to say as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y will approach negative infinity. Okay, so now let's go ahead and try and find x-intercept. So we set f of x equal to 0 and solve for the roots of this equation, and we get x equals to 0 and -3. So those end up corresponding to our zeros. And let's also state the multiplicity of each zero. So the multiplicity of 0 is 2, and the multiplicity of -3 is also 2. So we have our x-intercepts. And then referencing the multiplicities, both of these zeros have multiplicities, even multiplicities. That means that at each of these x-intercepts, the graph will end up touching the x-axis, but it will not cross. And then note that there's only going to be one y-intercept for a polynomial function, and that y-intercept occurs at 0, 0. It's also an x-intercept. So let's graph what we know. Okay, so we have 0, 0, -3, 0, label a little bit. Okay. So I graph my x-intercepts, and I know the end behavior is going to be both ends up. So I know that to the left of -3, 0 and to the right of 0, 0, the graph is not going to come back down and cross the x-axis. Again, it's just going to keep going up and up and up. Okay, we also know that the graph is going to just touch at each of those x-intercepts. So that means that it'll come down and then curve up again at -3, 0. And it'll go up, and I don't know how far it'll go up before it comes back down again to then bounce back off of the x-axis at 0, 0 and go back up again. So here's where you could do test points. You could do a test point between, find a point between -3, 0 and 0, 0 by picking like, I don't know, like -1.5 to evaluate the function at and find the y value that goes with it. However, that does not guarantee you're going to find the highest point on this curve between the two x-intercepts. It would just give you a little bit better idea of what the graph looks like, but you actually need calculus in order to figure out what the highest point between these x-intercepts is going to be. So for now, we're just going to use our end behavior and x-intercepts, y-intercept, and multiplicity to help us sketch what the graph looks like. And then next year with calculus, you'll be able to sketch some more accurate looking graphs. And we can compare this. We can use Desmos to check that our graph looks kind of close to what it should. Okay, so if we zoom out a little bit, yeah, we can see that it looks kind of like a round W, like what we have sketched. All right, so this next polynomial is not in factored form, so when we want to find our real zeros, we're going to need to factor. But just looking at that equation, we can see that the degree is also going to be 4, like the previous polynomial. And the leading coefficient will be a positive 2. So our end behavior will be, again, both ends pointing up. So as x approaches positive or negative infinity, y will approach positive infinity. Okay, so setting f of x equal to 0, can factor out the GCF of x squared first. And then that will factor to, 2x minus 1, x plus 3. So the roots to this equation, which will end up corresponding to our real zeros, are 0, 1/2, -3. Let's also state the multiplicities. So the multiplicity of 0 will be 2, of 1/2 will be 1, and -3 will be 1 as well. So 0, 0 is again going to also be our y-intercept. So because 0, 0 has a even multiplicity, right, a multiplicity of 2, we know that the graph will touch at 0, 0. And then at 1/2, 0, multiplicity of 1 means the graph will cross and cross again at -3, 0. So I'm going to sketch what I have. So put all the information together that we've collected in order to get an idea of what this graph will look like. Okay, so I'll start by plotting my x-intercepts. I know the end behavior. Okay, so at -3, 0, the graph crosses. I don't know how far it'll come down. It's going to go back up to 0, 0, bounce off of 0, 0, touch, and then curve back down. But again, I don't know how far it's going to curve down before it comes back up through 1/2, 0. So again, you could do test points to get a more accurate sketch of the graph, but I'm not requiring you to do that. Let's compare with Desmos. Okay, so here. So we can see that the graph ends up going down pretty far. So almost to -21. But then up here, where the graph, so between 0, 0 and 1/2, 0, the graph doesn't actually come down very much before it curves back up. So our graph actually is pretty accurate looking. In the shape, at least, right? That between -3, 0 and 0, 0, the graph comes down a lot more, but we have a general sketch. All right, so let's look at this last example. Degree is 5, right? I just looked to the largest exponent. Leading coefficient is just 1. So end behavior, okay, odd degree, positive leading coefficient, end behavior will be like a line with a positive slope. Setting f of x equal to 0. Factor out the GCF of x cubed. Then that's a difference of 2 squares. Okay, so we can see that the roots for this equation are 0, 2, and -2, which will correspond to being the real zeros. All right, 0 has a multiplicity of 3, which will make the graph kind of interesting. 2 has a multiplicity of 1, -2 has a multiplicity of 1. So listing my x-intercepts, 0, 0 is again also a y-intercept. Okay, so 0, 0, actually all of them have odd multiplicities, right? So at all 3 of our x-intercepts, the graph will cross. Okay, so graphing my intercepts. All right, I have an idea of what the end behavior should be. So at each of the x-intercepts, the graph will cross through the x-axis. So it'll go up. And here's kind of the cool part. Because 0 has a multiplicity of 3, the graph is actually going to cross through in kind of an S shape, like x cubed, like the graph of x cubed. Okay. If it just were, if 0 had a multiplicity of 1, it would just cross through straight. But it's kind of S-shaped because it has a multiplicity of 3. If it were a multiplicity of like 5 or 7, that S shape would become more and more flat. So let's compare. Let me first label the x values here. Okay, so let's compare on Desmos. And I'm actually going to type it in the factored form because I want to play around with the multiplicity then. Okay. Okay, so we can see that the graphs end up coming down a lot further for the maximum and like local maximum and minimum points and going up pretty far. Well, actually not that far. Okay, but you can see at 0, 0, the graph crosses the x-axis in an S shape, like x cubed. And if I were to change that exponent to a 5, look at it, just becomes a more flat S shape, or even 7, even flatter, or 9, even flatter. Okay. But if it were just 1, then it crosses straight through. Okay, so we can see that graph looked somewhat like it. It's just that this actually ended up going up a lot further and down a lot further.